The title of my talk today is Minimum Dose Rate Required by Flash Radiotherapy. In radiotherapy, there are two probabilities we have to consider. One is tumor control probability, i.e. TCP. The other is normal tissue complication probability, i.e. NTCP. In general, tumors are more sensitive to radiation than normal tissues. So we have the so-called therapeutic windows between the two curves. It allows us to pick a dose that will produce a good TCP with an acceptable NTCP. Now imagine if we can keep the TCP curve stay at the same location while push NTCP curve towards the high dose side. We will end up with a much wider therapeutic window. Now we can achieve almost a perfect TCP with minimal NTCP with a higher dose. Ultra-high dose rate or flash RT has the potential to enable us to do so. The differences between these two NTCP curves are observed in recent studies. In this slide, I show you some milestones related to flash study. The first one is the oxygen effect. It was discovered in 1958 that radiation kills cells at different rates when intracellular oxygen tension is modified. Sudden drop in radiation effectiveness in bacterial cells and mouse experiment with flash irradiation were observed shortly after this study. Dewey and Borg might be the first group to suggest that radiation-induced oxygen depletion might be the root cause of such phenomena in 1959. Interest in flash RT resurged after European researchers reported greatly improved differential responses between normal tissues and tumors with flash RT, first in mice and then confirmed in minipig and cat. Finally, late last year, the first human patient was treated with flash RT on compassionate grounds. Let's examine one result from early flash irradiation experiment. In 1967, Towns performed cell survival studies with bubbling air or nitrogen through the cell suspension and observed this hockey stick-shaped cell survival curve. The lower portion of the curve has a slope similar to that of cells in hypoxic condition, suggesting cells are in hypoxic condition in the second phase. The oxygen depletion hypothesis is the following. Ultra-high dose rate radiation leads to significant intracellular oxygen tension drop. This results in reduced cell radiosensitivity. The first step can be described by radiolysis and oxygen diffusion theory. The second step has been studied extensively as the so-called oxygen effects in radiation. Next, we show you how to characterize ultra-short radiation pulses. Because the pulse with W is so small compared to any other time scales in the study, so we can ignore it. That leaves only two variables to consider. One is the dose per pulse. The other one is the pulse period between two adjacent pulses. We denote it as T. The dose rate R equals dP divided by T, which is the conventional definition or a time average dose rate. To search for the minimum dose rate, if we can vary dP and T independently, this minimum dose rate would be the minimum dose per pulse required divided by the maximum time interval between pulses allowed by flash RT. Next, we want to give you the results from a radiology study. Basically, the drop in intracellular oxygen tension is proportional to the dose it receives, and G is constant. This step happens in a time scale of 10 to the minus third. Next, we want to explain diffusion-limited oxygen restoration. Most living tissue cells lie within 1 to 3 cell width of the capillary. Therefore, the distance from a cell to its nearest capillary is in the order of 10 microns. When radiation-induced oxygen depletion happens, oxygen molecules from surrounding high oxygen tension regions, particularly from nearby capillary, will diffuse back into this oxygen depleted region. According to the physics law of diffusion, tau, the characteristic time for oxygen molecules to travel over distance L, is of the order of L squared divided by D. Here D is the oxygen diffusion coefficient. It has been known for a long time that oxygen can enhance radiation damage to cells. It can increase cell radiosensitivity by a factor of 2.5 to 3 when cell environment changes from hypoxic to aerobic. The relationship between cell radiosensitivity and oxygen tension can be well described by the following formula. In general, in vivo tumor cells are in hypoxic condition, and the normal tissue cells are much better oxygenated. This provides a good explanation why flash RT affects normal tissues much more than tumors. Next, we estimate the minimum dose per pulse required to produce observable flash RT effects. Based on the formula I just showed you in the last slide, in order to achieve 3% relative radiosensitivity drop, dP must be at least of the order of 0.2 divided by 10G. The minimum is realized at the point in the steep sloped region. We tried other thresholds from 3% to 10% and found out similar results. dP minimum is on the order of 3 gray. Next, we consider pulse period time T. When T is much smaller than tau, the cell experiences the reduced oxygen level all the time, and flash RT effect probably can be easily achieved. By contrast, when T is much larger than tau, the cell only spends a small portion of time under the reduced oxygen level. Most of the time, it stays in the same oxygen condition and does not feel the radiosensitivity change. Therefore, makes it harder to observe any flash RT effect. So the turning point of flash RT effect is when T and tau are of the same order. Now T is short enough to just suppress the oxygen surge due to diffusion from capillary to avoid the cell spend a long time under the O2 level prior to post-irradiation. Putting everything together so far I described, we get the order of magnitude estimation of R mean, which is the ratio between dp mean and T max. Plug in all the coefficients, relevant coefficients, we can get the estimation of the dose rate, minimum dose rate, which is about 57 gray per second. By the way, this is consistent with the experimental observation of R minimum around 40 gray per second. In summary, there are three keys to achieve observable flash RT effect. One, high enough intracellular oxygen tension. Usually normal tissues satisfy this requirement, but not for tumors. Two, short pause period. That is one of the flash RT characteristics, and not for conventional RT. And third, high dose per pulse. Minimum of 3 gray of dose must be delivered per pulse to cells. The last two combined will set the lower limit for dose rate for flash RT. Next, the last slide is an acknowledgement slide. I want to thank my colleagues for their contribution, and also the research results reported here was published in a recent paper. Thank you.